So we want to look at 4 different scenarios that an elevator rider may find themselves in. So we'll just call it living in an elevator. And so in the first situation, oh, by the way, this elevator rider has a mass of 80 kilograms. I should say that up front, because it tells us a little bit about the rider himself. And I will say himself. This is a guy. This is a man in an elevator. A real man. Whatever that means. And he's got an initial velocity in the first situation. An initial velocity, I should say like an average velocity, of 0 meters per second. And he continues to have that velocity. It's a valid velocity. 0 meters per second means he's not moving. And if he's not moving, you tell me. What's his acceleration? 0. Yeah, that's easy. 0 meters per second squared. And I don't even have to assign a direction. Although speaking of directions, I think I'd like to call up positive and down negative. Just for kicks and giggles. But I would like to find the force due to gravity acting on this gentleman. How could I find the force due to gravity acting on the gentleman?
Acceleration due to gravity at the general, at this level.
Yeah, mass times acceleration due to gravity at this latitude, at this location. Happens to be 9.81 meters per second squared where this fellow lives. So 9.81 meters per second squared times 80 kilograms. And I've done this math already. It was 784.8 newtons. So I'm not going to labor the point by actually taking too much time on that calculation. That's the force due to gravity acting on this guy. I could figure out his net force. And I could do that by doing mass times acceleration. What is his net force? His mass times his acceleration. That's right? Yeah, it's 0. Because he's got an acceleration of 0. So anything times 0 is 0 newtons. And I would also like to find his normal force. But I know, and I'm going to think in terms of a free body diagram here, I know that if I draw his free body diagram, all the forces acting on this guy, and now this rectangle represents the man, not the elevator. I want to be perfectly clear about that. This rectangle here is not the elevator, but the man inside. Okay? The man inside is this rectangle. And I have the force due to gravity acting on this guy. It happens to be 784.8 newtons. I suppose I could round it off and say that it's approximately 785 newtons if I'm going to 3 significant digits, because that's how many I have. 785 newtons approximately. And if I'm going to get a net force of 0, what's the normal force acting on his feet equal to? Sorry? Go on, somebody other than Jacob. Jacob's always whispering in my ear up here at the front. What's the normal force equal to? Yeah?
785.
Yeah, 785. F normal, 785 newtons, approximately, because we've already rounded off that value. We know it's closer to 784.8. 785 newtons. But instead of just making that observation, what I could have done is I could have written F net is equal to Fg plus F normal. We talk about setting net force equal to the free body diagram. And I could have said, F net is 0, but F normal is really F net minus Fg. In this case, F net being equal to 0 just means that F normal is equal to negative of the force due to gravity, which gets us to the same location. But it's worth noting that I can do it with an equation like that too, okay? And the reason I mention that is because it might be useful later on, not because I just think it's fun to point it out, okay? So in the second scenario, I want to build up the story again. Different story, slightly different story. This guy has a changing velocity, and this changing velocity is such that his acceleration, the acceleration of the elevator, the man, and anything else that happens to be inside the elevator, is 5.00 meters per second squared up. Or I could say positive 5 meters per second squared if I keep the same frame of reference. Positive 5 meters per second squared. It's the same guy, so what's his force due to gravity, approximately? Yeah, 785 newtons. We're just going to round it off. 785 newtons down, or we could say negative 785 newtons. And later on when we do some math, we will say negative 785 newtons. The next piece of information that I might note is the net force. How could I find the net force on this young man? How do you find net force on an object? You could use free body diagrams, but there's another way sometimes. Taya, what do you say? Anybody want to rescue Taya? Yes, ma'am?
Physical acceleration times mass.
Yeah, the acceleration times the mass. And in this case, mass times acceleration of the system, or even mass times acceleration of the man, which is the same as the system, is going to be 80 kilograms times 5 meters per second squared. And if you can do a little bit of head math, you know that 80 times 5 is 400. Yeah, 400 newtons up, or positive 400 newtons is the net force on this fellow. Now I'd like to get down to the point where I know the normal force on this guy. Okay, so the normal force, I could get at it. I can't say this time that the normal force is equal but opposite to Fg, can I? I don't think so. What I can say, if I look at the free body diagram, so I'm going to draw a free body diagram down at the bottom, is that I have an Fg and an F normal. I'm not drawing the arrows to scale because I don't know all their values yet. Fg equal to 785 newtons. I agree with that. F normal, I don't quite know yet because I'm not going to assume that it's exactly the same as Fg but in the opposite direction. What I could say is that F net is equal to, I'm setting the F net equal to the picture again, F normal plus Fg. Can you see that that's the equation still? There's nothing different here. This time though, F net isn't equal to 0 like it was in the first scenario. This time it's equal to 400 newtons up, positive 400 newtons. So if I want to know the normal force, I have to get F normal by itself. So I can say F net minus Fg is equal to the normal force. And if I sub in my values, I can say that F normal is equal to, well, F net was positive 400 newtons, okay, 400 newtons, and minus Fg, so minus, remember, the Fg was down, so it's negative 785 newtons. 400 newtons minus negative 785, really, negative, a minus a negative is a positive, so what's the normal force equal to?
1185.
Yeah, 1,185 newtons. And, if I was going to those three significant digits again, I might be tempted to say 1,190 newtons, but I think I'd be satisfied with understanding what went on here. Okay? So that's the normal force. You notice that the normal force is not the same in the second scenario, but the free body diagram and the equation for the free body diagram, F net equals F normal plus Fg, is the same. And that's okay. Just, it's a different situation. It's a different story, and I got to be able to tell the story. So here's a new story. We're telling 4 stories. Each one's going to follow the same basic story line. Similar plot, different details. Okay? Here's the new plot twist.
Storybook for bedtime.
Yeah. The new plot twist is that this fellow has a constant velocity of 5.00 meters per second up. Constant velocity. Now that's a key word in this explanation, and you've encountered that before in homework questions. If you have a constant velocity, tell me about the acceleration. 0. Yeah, you got it. No velocity change means no acceleration. So acceleration is 0 meters per second squared, and no direction required because it's 0. So if I want to find the F net for the rider, what is it? 0 newtons. Okay? And now it's looking sort of similar to situation 1, only I'm moving this time. So a little bit of a plot twist, but it sort of still makes sense, right? And I say, I would really like to know the normal force, and I know that a key in the past has been to say F net is equal to F normal plus Fg, because I know Fg. Fg is still going to be equal to 785 newtons. So maybe I could make a note of that. Fg is still equal to 785 newtons. Maybe I could have written it below as I did before, but I got distracted. If I want to get the normal force, though, let's write F net minus Fg is equal to F normal. Now, F net is equal to 0, so I could say, all right, F normal is equal to negative of Fg, which is actually negative 785 newtons, because gravity is acting downwards negatively, okay, acting downwards or negatively. So I could say that normal force is going to be positive 785 newtons. I think that sort of makes sense. Like if I'm not accelerating, the normal force shouldn't be any different than if I'm sitting still. Okay? So we've got our Fg, 785 newtons, and our normal force. If I'm going at a constant velocity, the normal force should be the same as if I'm sitting still at a constant velocity that happens to be 0. The logic doesn't change. That's the beautiful thing about this stuff. The logic never changes. It's the same thought process each time. Because the rules are always the same. It's just the story that changes. Alright, my fourth version of the story. I want to accelerate again, similar to in situation 2 maybe, a little bit. I want to accelerate at 5.00 meters per second squared, but this time down. Okay, so a negative acceleration. Right? So again, force due to gravity hasn't changed. It's still 785 newtons down.
That was before the newtons.
Yeah. And F net has changed. How can I calculate F net?
You can just take it from
Mass times acceleration, right? Okay, so mass times acceleration, 80 kilograms times 5 meters per second squared, 400 newtons. Makes sense. 80 times 5. Mass times acceleration. Same as I did before, except that the acceleration is down this time. So I say 400 newtons, but this time down. And you know, it's okay for an elevator to accelerate downwards. I mean, it's accelerating downwards at 5 meters per second squared, not at as high a rate as gravity. What acceleration would you experience if somebody cut the cable? Yeah? Well, that would be the force of gravity. But what would your acceleration be if somebody cut the cables? Kara? Yeah, 9.81 meters per second squared. Yeah, that's exactly right. If somebody cut the cables, that's what you'd feel. All right, what acceleration you'd experience, rather. We're not experiencing 9.81 meters per second squared, so we're not in free fall. Nobody cut the cables. We just happen to be accelerating a little bit as we're traveling down. That happens.
One of those movies, elevators.
Yeah, you can have spooky elevator movies. Surely. There could be a spooky twist to this story. We're not going to make any spookiness. This is just a regular old elevator that has some sort of a drive motor that lets us go downwards with some acceleration, okay? So, keeping up with this story, I would like to figure out what the normal force is on the person's feet. So I'm going to draw the free body diagram as I try to answer or tell the story. And again, the force due to gravity acting on this person hasn't changed. He's still on Earth, 785 newtons. And I want to find the normal force, but I don't know the value yet. But what I do know, just like I knew before, is that F net can be set equal to the picture. No funny business. Yes, Garrett? Oh, you jump right to the answer. Come back to me in a minute, okay? So I can say F normal plus Fg, and just like we did before, we can get normal force all by itself by saying F net minus Fg is equal to F normal. And subbing in our values, we can get F normal is equal to F net, which this time was negative 400 newtons, minus the gravitational force, which again is a negative value, negative 785 newtons. So negative 400 minus negative 785 newtons. And what do you get, Garrett? Yeah, you got it. Positive 385 newtons. Or we could say that the normal force is 385 newtons up. Okay, so if we were talking about this story in terms of really experiencing it, lots of us have been on elevators. I have frequently been on elevators. And what I've noticed is that when I'm sitting still in an elevator, it's like I'm sitting still on regular ground. Have you noticed that? It's a nice thing about a good elevator. It shouldn't be that different, right? What I've also noticed is that if I'm moving along, like, you know, if you've ever been to CN Tower or any long elevator ride, as you're moving along, you typically feel like, you know, midway up the tower, you feel like you're standing on regular ground. Doesn't bear that much difference to standing on the ground. What I do notice, though, and, you know, maybe I noticed it more when I was a little kid, but when the elevator first kicks in, you know, the doors close behind you, you press your button for what floor you want to go to, you know, the engine engages, and the elevator sort of leaps into action. I remember when I was a kid feeling my knees buckle just a little bit. You know what I mean? Like, you sort of feel an extra pressure on your feet when the elevator jumps into action. And I think when I was a little kid, maybe I wasn't very good at anticipating when the elevator was going to start. Maybe now there's these little subtle clues in the background. You hear the engine, you hear a little whir of the motor, and you sort of brace for it a little bit. Maybe you just subconsciously. But when I was a kid, I do remember, just a little bit, I remember my knees buckling a little bit. And it's because the normal force was increasing as the engine engaged, as the acceleration sort of started. Can you sort of picture that? Just for a moment. The same thing's true, though, if you're at the top of a building. And in that instant, when the engines engage and the floor sort of falls out from underneath of you just a little bit, or at least accelerates downwards a little bit just for a moment as the elevator gets up to speed. Maybe when I was a little kid, I do remember it, faintly. I don't seem to feel this anymore, but I do remember when I was a little kid feeling butterflies a little bit sometimes in the elevator. You ever felt that in an elevator or even on an amusement park ride? You start downwards, you weren't quite anticipating it, and that little change in the normal force, it's a little bit of uneasiness, but that change in the normal force, it's a change in the sense that you're accelerating downwards, and your body sort of responds to it. Okay? So I've experienced this before, but now I have the ability to sort of lay it out in free body diagrams and figure out, well, how is that force changing? How's the pressure on the bottom of my feet changing? And there might be some other, this might be like a sensory thing. This could be a region of discussion for biology people or something. But it also seems to be a region of discussion for physics people too, right? There's free body diagrams we can look at here. And sure, the senses play a role in giving you butterflies and your knees buckling and all that sort of stuff. But definitely some physics. And it's worth having a discussion about.